So as we have seen in the previous video, memory is one of the most important things because all your programs are actually stored in the main memory itself. So whenever we say memory, we are referring to main memory. Whenever we say disk, we are referring to the secondary memory. Okay, let's use that as the standard terminology. So all programs that the computer or the CPU executes are in memory, right? They have to be first loaded into memory. Only then we start executing them. This is very important. Again, let me write down a bunch of key points here. Now, if you look at it, you can think of memory logically. You can think of memory logically like this. Again, I'll also show you a chip diagram on how memory looks like. You can think of memory literally as a series of, so each of this is called a cell. Each of them is called a cell or a word or a location. Right? Each of them. So look at this. Your memory itself can be thought of as basically having addresses. Again, this address itself is the logical address. Okay. So if you think of this as your whole memory, you can say if the CPU wants some data. Okay. If the CPU wants some data, the CPU can say, I want the data from cell 4 or from location. This is also sometimes called as location. Okay. Or word. Okay. The CPU can say, I want the data from cell 4. Okay, then whatever is the data that is there in this cell is sent back to the CPU. Right? So, or the processor. So, I'll use the word CPU and processor interchangeably. Right? So, every memory cell or every memory word or every memory location has a unique address. For example, this has an address 4. Imagine your whole memory has n cells. If your whole memory has n cells or n locations, the addresses start from 0, go up to n minus 1, right? So what the CPU does is, again, I'll show you the chip diagram also. This is a logical way of understanding the main memory, right? So the CPU sends a couple of control signals. There is something called as control signals. These are called as control signals, right? The CPU sends to the main memory chip saying either it wants to read the data, which means it wants to obtain the data from the main memory, or in this case from the RAM to the CPU. That's what it means when it says I want to read. Or the CPU can say I want to write. So read and write are two of the very important control signals, because using this you control the flow of data into the RAM or into the main memory or out of the main memory. Right? So that's how it works. Now you also have address. The CPU also sends the address. The CPU says I want to access, or let's say it could say I want to read the data which is at address 4. So the CPU sends the control signals and the address. Now when the CPU says, let's say I want to read the data from address 4, then what happens internally in the actual main memory chip or the RAM chip is whatever is the data stored at location 4, that whole data is sent to the CPU. See, the data is sent to the CPU now. Right? On the other hand, if the CPU says, I want to write data, I want to write some data at, let's say, address, 6. Okay. Then what happens is the data comes from the CPU. Whatever data came from the CPU, it gets written into this location. Right? So that's how logically a memory actually works. And whenever a CPU typically performs something called as memory requests. Right? So CPU performs memory requests. Okay, and how do these requests look like? The CPU memory request itself looks like this, right? So you have the address, basically, which means at what location do I want to read or write from? And there are also control signals, right? Do I want to read the data or write the data? If I want to write the data, the CPU also gives the data that has to be written into this location. Okay, so that's how actually your CPU and memory communicate. They communicate using the actual address of the cell, word or location and using the control signals. Right? Bottom line, that's how it works internally. Again, we'll see some actual chips to understand how everything actually fits together. Right? So now let's look at memory chip internals. Okay, this is the logical view. This is how you can imagine or logically think of memory or RAM. Or main memory for that matter. Now, how does it look internally? If you look at any memory chip, so for example, I'll show you this chip. This is one of the very popular memory chips called 6264. This chip number is 6264. Look at this. This chip number is 6264, right? So this is actually a memory chip. Again, we'll understand how the chip itself works. But if you have a chip, if you have a memory chip, okay, again, this is the actual chip view of things. Chip has these pins. Okay, each of these chips has these pins. We'll explain what each pin does and all of that in a little while, right? But broadly speaking, what does a chip store? Chip at the end of the day stores data. So on every chip, you can see something like this mentioned. If you go and read, look at this. If you have any chip, pick any memory chip of your choice, right? So they have something called as a data sheet. So if you just Google search and say, I want the data sheet for this memory chip named 6264. Every memory chip has a unique number like this, right? So this chip number is 6264. You can ask for data sheet. If you go and look at the data sheet, it clearly tells you that this chip or any chip has this type of configuration. Okay, or this says this chip is 64K cross 16. What does this mean? This means, see, the first number 64K, this is your N, or in other words, this is the number of cells. This is the number of cells. Okay, this 16 here is the size of each cell, is the size of each cell in bits, right? So literally what this 16 is, the 16 is how much data is stored in each cell. So 16 bits of data can be stored in each cell or each word or each location. Okay. So whenever you're given a chip which says 64K cross 16, it means it has 64K cells and each cell can occupy 16 bits. Now comes a very interesting question. So imagine if I have a chip like this. Okay. Again, some chips you can also have 64K cross 32. This is clearly mentioned. Okay. So let's take this chip. Okay. So in 64K, so you have 60, look at this. You have this whole, you have this, how many addresses are there? 64K addresses are there. Look at this, which means you have numbers from 0, 1, 2 up to 64K minus 1. Those are the address numbers, right? Now to represent 64K unique values, remember every cell has a unique address. To represent 64K values, how many bits do you need? See, every bit, look at this, every bit can store 2 values. Every bit can store 2 values. So how many bits? So if you have 2 bits, let's say you may have 2 bits. How many values you can store in this? 2 square. If you have 3 bits, how many values can you store? 2 power 3. 2 values here, 2 values here, 2 values here. Right? If you have 4 bits, how many values can you store? 2 power 4 values. Now what should be the size of this address? Okay, that's what we're trying to figure out here. Now, what is 64K? Now, in a whole of computer science, this is very, very important thing for you to get your head around, right? 1K basically means 2 power 10. Okay. 1 mega, 1 kilo basically means 2 power 10. 1 mega basically means 2 power 20. 1 giga basically means 2 power 30. 1 tera basically means 2 power 40. Now, if you notice, 2 power 10 is 1024. 2 power 10 is 1024. This is approximately equals to 10 power 3. Right? Similarly, 2 power 20 is approximately equals to 10 power 6. 2 power 30 is approximately equal to 10 power 9. 2 power 40 is approximately equals to 10 power 12. So 1K is approximately equal to 1000. 1 mega is approximately equal to 1 million. 1 giga is approximately equal to 1 billion. 1 tera is approximately equal to 1 trillion. Approximately, not exactly. Right? So I hope, again, this is something that we'll keep using. Now I have 64K. What does 64K basically mean? So let me erase this space and use this. Okay. So my addresses will range from 0 to 64K minus 1. Now what does 64K actually mean? 64K is, what is 64K? What is 64? 2 power 6. Again, it's very important for you to know 2 power 1, 2 power 2, 2 power 3, 2 power 4. You'll get used to it with some practice, right? 2 power 6 is 64. 1 kilo basically means 2 power 10. So this is 2 power 16 cells. Look at this. How many cells are there or how many locations are there? 2 power 16 locations are there. Right? So to address 2 power 16 cells, how many bits do I need? To address k bits, see, you need k bits to create 2 power k unique values. Right? You need k bits to create 2 power k values. So you need 16 bits to create 2 power 16 unique addresses. Right? For 2 power 16 unique addresses. So this address itself is 16 bit. So we write it like this. So If it is 1 bit, we write it using just one line. If it is 16 bits, I write it using this. So we cross it and we put 16 here. This means this is not one line, but these are actually 16 lines. So to your memory chip, there have to be 16 input lines. Okay, each line can represent, again, remember, each of these wires or lines can represent only 1 or 0 because they represent bits, right? Very simple concept here, right? Because I have 64K, look at this, because we have 64K addresses, we need 16 bits to address it. And how did we know that? Because 64K is 2 power 16. Now look at this. Now the second part here, this is also 16, which means any data that I transfer to the CPU, any data that I transfer to the CPU or that I get from the CPU to write or read to this memory chip, this has to be 16 bits. So this data is also a 16 wires. So this is called the 16 wires which go to the CPU, literally. That is called as the data bus. This is called as a data bus because it is a collection. The word bus here basically means it's a collection of wires. So this is called the address bus. This is called the address bus because instead of one wire here, you have 16 wires. So if you have a 64K cross 16 memory chip, what you have here is you have an address bus of 16 wires or 16 lines, and you have a data bus of also 16 lines. Imagine on the other hand, if you had a chip which is 64K cross 32, then since the number of cells do not change, the address size doesn't change. But the word size or the cell size or the location size is 32 here, which means this width will become 32, which means the data bus width will become 32. Okay, that's how you understand this number. This is a very, very important number. Given any memory chip, we are given this information and it helps us understand how many address bits are there, how many locations are there, or how many cells are there, or how many words are there. And it tells us what is the size of or what is the width of the data bus. The width of the data bus is equal to the number of bits we can store. Again, this is also sometimes referred to as word width. This is also referred to as word width because this is the number of bits that I can store in one word, or it's also sometimes referred to as cell width or location width. Remember, cell, location, word are used interchangeably. Different books use different names, but all three of them are valid names. Okay. So now I hope you understood how we actually address memory and how to compute. Given this configuration of memory, we need to understand how many address bits are there, what is the size of a data bus, and how many locations are there, right? So oftentimes in practice, instead of having 2 wires for read and write, what typically happens is you just have 1 wire typically. On many chips, you just have 1 wire. This is often written as read by write bar. So what this means is if this is 1, if you're sending 1 through this, see what is 1 in digital logic circuits? 1 basically means plus 5 volts, right? 0 basically means 0 volts, right? That's what it means, right? This is something that you may have learned in your digital logic circuits. If you're sending 5 volts of electricity through this, that means it's now in the read position. So 1 basically means read. So 0 basically means write. 0 basically means write. That's where write has a bar on top of it, which means this is active when this is low. Again, 1 basically means high. 0 is often referred to as low. Okay. So again, from a pure electronics perspective, 1 in binary corresponds to 5 volts. 0 in binary corresponds to 0 volts of electricity that is being sent through this wire, literally. Okay. If you want to look at it from the electronics perspective. Okay. So I hope this part of it is clear and easy to understand. Now let's see how the whole addressing itself works. Again, many times, look at this. Here we have 16-bit addresses, right? A very important point here is instead of writing all the 16 bits. Okay. So let's also understand that concept here. Imagine my address is 1011 1100 0001 1100. So this is 16-bit. This is one of the addresses, right? So this is in binary. This is one of the binary numbers, but this is too cumbersome to read for humans. So you see in many textbooks, even when we are discussing, instead of writing this in binary, we write it in hexadecimal. Again, we discussed about binary and hexadecimal multiple places, right? We discussed how to convert from binary to hexadecimal when we learned C programming in our digital logic circuits and design, all of these subjects, right? So oftentimes, instead of writing it in binary because it's too lengthy, people often write it in hexadecimal, right? So how does the hexadecimal work? Look at this. What is this? So this is 1100. Okay. So we write the corresponding hexadecimal. It will be one digit. We write the corresponding hexadecimal for this. The corresponding hexadecimal for this. The corresponding hexadecimal for this. Right? Hexadecimal is base 16. So you get a 4-digit base 16 hexadecimal number. So in many books and in many data sheets for many chips, instead of writing this information in binary, they write it in hexadecimal, right? Hexadecimal basically means base 16. What all numbers does it have? It goes from 0 to 9, A, B, C, D, E, F. Okay, this is how hexadecimal numbers look like. Okay, let's actually do it. Okay, what is this? What is this in binary? 2 power 0, 2 power 1, 2 power 2, which means 2. Okay, 2 power 2 is 4, 2 power 3 is 8. So this is 12. What is 12? A is 10, B is 11, C is 12. So this is C. What is this? This is 1. This is literally 1, right? 1 in binary and 1 in hexadecimal is just 1. So what is 1100? 1100 is 2 power 0, 2 power 1, 2 power 2 is 4, 2 power 3 is 8. So this is 12. What is 12? 9, 10, 11, 12. So again C. What is this 1011? 2 power 0 means this is 1, 2 power 1, this is 2, 2 power 0, 2 power 3, 2 power 4, 4, 5, 6, 7, right? 4, 5, 6, 7. So we just write 7 here. So this binary string, this 16-bit binary string is converted into a 4-digit hexadecimal string. We either write base 16 or sometimes people also write 0x to represent that this is base 16. Okay, so instead of writing this big string, we have just gotten away by just writing 4 symbols here. Right? Again, to understand how binary to hexadecimal conversion works, please check out the videos from C programming or digital logic circuits. Right? Very simple concepts here. Now, how does the whole address decoding work? Till now, what I've been telling you is, you give it an address, it gives you data. But how does the internal circuitry work? Okay, at a high level. So what happens is this is very, very interesting. So you have something called as a 16-bit address register. So the 16-bit, look at this, the CPU sends 16-bit address. Look at this, the CPU sends 16-bit address, right? That 16-bit address is stored in a memory location called the address register, right? So this is 16-bit. So the address is stored here. The address is given as an input to the address decoder. Again, you must have learned about decoders in digital logic circuits and design. Okay, in digital logic circuits, right? So what does a decoder do? Again, this decoder has 16 inputs. Remember that there are 16 wires as inputs here. How does a decoder work? The decoder has 60. This decoders typically come in this way. If it has n inputs, it has 2 power n outputs. Okay, decoder. So this is how a decoder works, right? If you've forgotten how a decoder works, let me give you a quick recap. This decoder has 16 inputs. So when I draw this line and say 16, it means it has 16 wires that come into it. Because it's a 16-bit address, right? So it takes the 16 bits. Now the 16 bits can correspond to, look at this, the 16 bits can correspond to values 0, 1, 2, so on so forth up to 2 power 16 minus 1. See, each of these, whatever input I get, right? What are all the addresses that can be generated? It could be 0. If all the 16 bits are 0, it is 0. If the 16 bits are like this, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay, if the 16 bits are like this, it means it corresponds to value 1. If the 16 bits are like this, look at this, if the 16 bits are like this, it corresponds to address 2. If all of them are 1s, it corresponds to 2 power 16 minus 1. So whatever is the 16-bit input, this has, again, this is the input. To my decoder, this is the input. My output of the decoder consists of 2 power 16 lines. Look at this, my input consists of 16 lines. That's how a decoder works, right? My output of the decoder has 2 power 16 outputs ranging from 0 to 2 power 16 minus 1. So how many outputs are there? All these are the outputs of my decoder. Now let's assume I input 0. I input all zeros here, the 16 zeros. Then it will output 1 from here. 0 from everything else. Only one output is high. At any point of time for a decoder, only one output is high. Rest everything is 0. Suppose my 16 bits are like this. Then only output 1. This output line is set to 1. Rest everything will become 0. So given any 16-bit address, only one of these output lines is high or active. Look at this, only one of them. When I say high, I mean it will be set to value of 1. When I say low, it means it will be set to a value of 0. Or active, I could use these words high or active, or low or inactive, right? So for example, let's take this simple example, right? Imagine I set this. Imagine my 16-bit address register has this value. These 16 bits are sent as input to the address decoder. Now, what does the address decoder do? Because this corresponds to binary, it corresponds to decimal value 2 power 0, 2 power 1, right? It corresponds to 2 power 1, which is 2, right? So this corresponds to a value of 2. So only the value 2, sorry, only this, my bad. Okay, so let me just erase this. Okay, so let me just erase this. Okay, so only this line 2 here, line 2 is set to 1, rest everything is set to 0. When line 2 is set to 1, whatever data is there in cell 2 or word 2 now gets loaded here. So this line basically says, this line is, see, this 2 goes here, right? Whenever this is high, or whenever 5 volts of electricity passes through this, there is 5 volts of electricity, right? Then this cell becomes active. Now, when this cell is active, all the other cells are inactive because they got 0 volts. They got 0 volts, right? 1 basically means 5 volts, remember, from electronics perspective, right? So 0 basically means, binary 0 means 0 volts. So what happened here? I gave a 16-bit address, or I gave a 16-bit input which corresponds to binary 2. So only this output 2 is active, rest everything is inactive. Because only this is active, this cell becomes active, this cell becomes active. And whatever data is there in this cell gets copied to this, gets copied onto this wire. Again, this wire is 16 bits. Okay, this wire could be 16 bits. Again, I'm assuming here that my chip is 64K cross 16. Okay, I'm assuming that my chip is 64K cross 16. So this 16 bits, whatever is the data stored here, let's assume this data is 16 bits, right? So this 16 bits get copied onto this line. Remember, all of them are inactive. This is inactive, this is inactive, this is inactive. Only this cell is active. So the data which is 16 bits here gets copied here, and this data is taken by a wire to the CPU. Okay, this is how it works. This is how address decoding logic works. Again, you may have learnt about address decoders in digital logic circuits, and you may have wondered, why do we need it? This is the reason why we need an address decoder, or decoders for general. You might have learned about general purpose decoders, right? One of the biggest applications of decoders in computer architecture is address decoding, right? So all this, remember, all of this is inside the actual chip itself. All of this logic is inside this chip. So when you see a physical chip, look at this. This is a physical chip. Each of these are called as pins. Each of them are called as pins. You can actually plug this chip onto a breadboard, okay? Or you can actually connect them using your printed circuit board. You can actually take wires and connect them to whatever you want. Look at this. This is called, look at this. If you look at the data sheet of 6264, this is called as a pin diagram. This is called as a pin diagram of 6264. Now look at this. 6264, you have this A12. See, look at this. It says VCC means power. So the power to the whole chip plus 5 volts. Okay, usually plus 5 volts. Look at this. It's written here. So plus 5 volts of power has to be given so that the whole chip has some electricity to work with. Okay. Then look at this address bus. It says address bus is A0 to A12. Look at this. I have from A0 to A12. Okay. So look at this. A0, A1, A2, A3, A4, A5, A6, A7 is here. Where are A8, A9, A10? Look at this. A10 is here. So these chips, so if you want to see, this has 12-bit address, right? So it has 12-bit address. If it has 12-bit address, how many memory locations are there? 2 power 12 memory locations, which means 4 K, right? Because this I can write it as 2 power 2 into 2 power 10, right? 2 power 10 is 1 kilo, 2 power 2 is 4, right? So how many address locations are there on this chip? 4K address locations are there in this 6264 chip, right? Very simple. Now, actual physically, if you, the A0, right? You have 12 bits, right? You have these 12 bits, right? So look at this. You have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. The 0th bit has to be connected here. The first bit has to be connected here. Second bit. So from the CPU, when you do the actual connection, you have to physically connect the 0th bit here, first bit here, second bit here, and so on and so forth. Now, what is the size of the data bus? Look at this. It says the data bus here is D0 to D7. Where is, so D0, D1, D2. Again, this goes to the ground. Ground basically means 0 volts. This 14th pin here. So here is your power plus 5 volts. This is ground, 0 volts. You need both of them for a chip to work, right? So this is, again, in electronic circuitry, if you have ever studied electronics, you send 5 volts of electricity. You connect this to 5 volts power supply. You connect this to the ground, right? Ground is often written as this in electronics. Okay. So now look at this. Your data bus itself is 8 bits. So D0, D1, D2, D3, D4, D5, D6, D7. Since there are 8 lines here, what is my data bus size? 8. So what is the whole chip? The whole chip is 4K cross 8. Look at this. There are 4K words or cells or locations, and each word, cell or location is 8 bits. That's because the data bus is like this. Now look at this read write. Look at this. Here is your read write that we are talking about. Instead of having 2 wires, here it has 1 wire. It says if it is high, it is read, which means 1 equals to read. If it is low, it means write, which means 0 equals to write. That's what it means, right? Again, every chip has some control bits. So this is called as a control bit. This is called as a control bit. We'll study about control bits little later. Again, there is this chip, there is this line called NC. This is not connected. We don't have to connect this to anyone. We can just ignore this. This pin was added just for symmetry. Okay, this is useless pin. You can just ignore it. You don't have to connect this to anything. The control pins now, the control pins like CE2 and CE1. This has 2 control pins, right? CE2. Oh, there is only 1 control pin. I'm sorry. Okay, so there is only 1 control pin. Oh, so this OE basically means enable outputs. Again, we'll study all of them little later. This control chip basically says whether you want to use this chip or some other chip. Again, we'll look into it little later. Don't worry about OEs and control pins right now. Rest everything I hope is clear from this diagram. Next, very importantly, very many times you might have encountered this term called 8-bit microprocessor, right? You might have encountered this. Again, please remember, there is a very important confusion that many people have. Physically, on the physical chip itself, the addresses are not there. Addresses are present in the logical view. These addresses are what we imagined them to be there. Physically, if you look at it, the chip doesn't store addresses, doesn't have addresses anywhere. This is cell 0. It only has the circuitry or the memory locations to actually store these cells. Which cell we choose is done using an address decoder. So the chip itself does not have the addresses physically. Addresses is what we logically imagine it to be there. And all that is physically implemented using an address decoder. So actually there is no specific address anywhere. There is an address register here. Whenever the CPU sends some address, it is stored here temporarily. And this is given as an input to the address decoder. The address decoder says which of these cells I should pick. And all the logic of deciding which of these cells to pick is done by the address decoder. Okay, that's a very important aspect. Many people get confused and many people ask, oh, where are these numbers 0, 1, 2 stored? They are not stored anywhere. They correspond to the output wiring numbers on the address decoder. Okay, so now that's good. So the next important thing is, many times you might have encountered this term called 8-bit microprocessor, 16-bit microprocessor, 32-bit microprocessor or 64-bit microprocessor. Again, very importantly, you might have seen Windows 64-bit. Okay, so this is something that you may have heard more often than the microbit, than the bit structure of the microprocessor itself. So when you install Windows, it says, do you want to install a 64-bit Windows or a 32-bit Windows? Even a lot of software that you install, it asks whether you want a 64-bit microprocessor, 64-bit Windows version or a 32-bit Windows version. What does this 32-bit, 64-bit here mean? So the Windows 64-bit basically means Windows 64-bit can only work on a 64-bit microprocessor. Okay, this only can work on a 64-bit microprocessor. Again, we write microprocessor in short like this because this is a symbol for micro, P means processor. A 32-bit Windows operating system can only work on a 32-bit microprocessor. Similarly, even software that are written for 64-bit may not work on 32-bit and vice versa. Right? So when you're installing Windows 64-bit, you need a 64-bit microprocessor to work. Okay. Again, there are ways to make 32-bit Windows to work on a 64-bit processor also. But typically, it's always optimal to install Windows 64-bit on a 64-bit microprocessor, Windows 32-bit on a Windows 32-bit microprocessor. Now, what does this 32-bit actually mean? Right? So now from the software perspective, this is the software viewpoint. This is the hardware viewpoint. Right? The 64-bit is nothing but the bit number of the microprocessor. If you have a 64-bit microprocessor, this means the word size. This means the word size or the cell size that this processor can operate with is 64 bits. Which means the memory, look at this. This memory has the output, right? This memory has the output. This means, see, what does this mean? A 64-bit microprocessor has memory with word size equals to 64 bits. A 32-bit microprocessor has memory with word size equals to 32 bits. Now what happens? So look at this. Imagine this is my RAM. Okay, let's take this simple diagram. Okay, imagine this is my RAM. Okay, data goes to my CPU now, let's say. Okay, if this is 64 bits, what does that mean? Which means the CPU can actually read this whole 64 bits in one shot. And it can process the whole 64 bits, whatever data is there in the 64 bits, it can process it in one shot. Which means your 64-bit microprocessors will be faster than or more efficient than 32-bit microprocessors. Because a 32-bit microprocessor can only read 32 bits of information in a single shot and process them. So 64-bit microprocessors are obviously more efficient because they can copy more data from the RAM and process this whole 64 bits in the CPU with single instructions. Okay, of course, today most modern microprocessors are either 32-bit or 64-bit. There used to be 8-bit microprocessors like 8085, 8086, very early microprocessors by Intel were all 8-bit microprocessors. Even 64-bit microprocessors were popular in the 80s and 90s, right? Currently, all the microprocessors that we use on most modern computers are 32-bit or 64-bit. Because, again, 64-bit is becoming more and more popular because 64-bit processors can process, so 64-bit microprocessors can process 64 bits of data. It can literally get 64, so the word size here is 64 bits. So it can grab all of the 64 bits and process all the 64 bits in one chunk instead of processing 32-bit, etc. Right? So whenever I hope what you have heard as 64-bit Windows, 32-bit Windows now makes far more sense after understanding about the 32-bit microprocessor, 64-bit microprocessor and how it connects to your RAM data bus size.